Trichloroethylene, also known as TCE, is a trichlorinated compound developed for use as a degreaser, refrigerant, and anesthetic. Most notably, it is a pervasive pollutant that poses significant risk to public health due to its carcinogenic nature and persistence in soil and groundwater. Making the issue of TCE pollution more pressing is that it was and is heavily used in numerous products such as Trichloroethylene, trouble-free rust buster, perfumes, pesticides, electronic components, and polymers. Due to its wide use, human exposure takes place in both industrial and household settings. From here, continued exposure can take place through leaching to the environment, where TCE can then enter the soil and groundwater, increasing the lifetime of this toxic compound. TCE poses a risk to public health because it can degrade to more hazardous compounds, in particular through biochemical pathways within the liver. Currently, the most efficient and cost-effective method for removal of TCE from polluted groundwater is air stripping. This method involves large volumes of air to separate the water from the TCE, and then it sends the TCE into the atmosphere, which can deplete the ozone layer. However, new restricted air emission standards may preclude the use of air stripping or otherwise require that off gases from them be treated by carbon absorption. In sum, this approach is simply transferring the trichloroethylene from one medium to another. Instead, the goal is to degrade TCE to harmless and simple compounds such as ethane. The insolubility and volatility of ethane allows it to be more easily separated from water than TCE in an air stripper. The less toxic and greener nature of ethane compared to TCE allows it to be released into the atmosphere, after which it can be completely decomposed to CO2 and water through combustion in a flare stack. A potential solution to convert TCE to ethane is to use nanocatalysts. Within the water filtration tank, the filter unit has slices of activated carbon filters supporting the nanocatalyst. In this case, the nanocatalyst is a bimetallic palladium gold nanoparticle chosen for its high surface activity increased by the catalytic activity of the palladium on gold. On the molecular scale, the palladium on gold nanoparticle absorbs the TCE, catalyzes conversion to ethane, and then the ethane is desorbed from the nanoparticle. Overall, the benefits of using this technology lie within the fact that we are converting TCE to a benign compound that poses no or little risk to humans and the environment, while creating less waste in the process. There may, however, be some environmental risk of nanoparticles being delivered to the contaminated groundwater. Little is known about their ecotoxicity, bioaccumulation potential, and persistence in the environment, and so more research is needed to elucidate the risk of their release into the water.